Hello and welcome again to my Physics Online video lecture series. In today's video we're going to be talking a bit about atomic spectra. Now a lot of what we do in this video would fit very nicely in the waves and optics part of our course, of our lecture series if you will. I'm basically going to use a diffraction grating. We've discussed this in a previous video about optics, and so in some sense like the demo works with optics, but it also kind of ties into some modern physics stuff with atomic spectra. Now at the moment I have my lights kind of dim because I actually have a little demo for today's video. I've got this carousel, and in this carousel there's a bunch of gas discharge tubes. I'm actually going to blow up the screen a little bit so that we can see the demo a little bit better. I've numbered these gas discharge tubes for my own convenience. So basically I can rotate this around and it's different molecules essentially. The gas discharge tube is just this glass tube that's filled with a gas or a vapor. And when I turn it on, I get basically a high voltage across the vapor, which tends to excite and or maybe even ionize the electrons within the atoms. And then they make collisions with other electrons in other atoms and excite them, and then those relax to a lower state and emit photons. And so basically when I turn it on, you get this nice brilliant light. And so this one right here actually happens to be helium. This one is hydrogen, and there's some interference pattern from the hydrogen, which I'm not actually sure about. I just saw that on the video today, so it's maybe something that I look into later, but if I kind of rotate it off, you can see the hydrogen fairly well. And then, oops, there's the little interference panel. I'll just leave it there for fun. So here's helium, here's hydrogen, this one's neon, this one right here is nitrogen, so it's the main element in the air that we breathe. This one right here is not seating well, This one, it should be water, but it seems to not be making good contact. That's okay. This one's air, not making good contact. This one is argon. Oh, so there's argon. Here's CO2. And here again is helium. And if I instead hold this little diffraction grating over them, you can see to the side these lines appear. If I hold it over the camera, then the lines are pretty consistent. So you can see these lines, and if I rotate it so that I have, this one's the CO2, you see that the lines have changed. Oh, now it's lighting up. This one is argon. Here's without, here's with. You can see that the lines have again changed. Guess it doesn't want to light up anyway. Helium, here's the hydrogen. You can see the lines. You can even see secondary maxima. And what I'll do is I will take a screen capture of this for discussion purposes in a minute. Here's neon. You can see lots of reds and oranges and yellows. Here is the nitrogen, and if we kind of look to the side, we can see the secondary, the n equals 2 lines as well as the n equals 1. and then this one wasn't lighting up for, oh, there we go. There's water. So here's water without, here's water with, and this one is not cooperating. This one would be air. Now, the main ones that I really wanted to look at today, though, was the hydrogen, which is this guy. So hydrogen, to a lesser extent, helium, argon, neon, nitrogen. These are basically single element atom molecule things, okay? So what we want is, in some sense, like just the line spectra that we're getting for hydrogen, and this is at 500 lines per millimeter of diffraction grating spacing, okay? And notice that these are in fact individual lines. Like if we look in here, this right here is an individual line. This one right here, individual line. This right here, individual line. We can contrast that with, let's say, a continuous source. So if I open up the windows, or if I turn on the light and look at that source through this, we'll see something a little different than those individual lines. Look at, for example, my overhead light through this and see what we see. So you can see individual bulbs. If I orient it with the bulbs, you can see that there's not really lines, there's just kind of continuous spectra of colors from this. So yeah, you can make out different colors, and yeah, it's a little complicated because it's several sources, not just one, but you are getting a spectra, not individual lines. So two of the main kind of take-home points on this little demo at this point, and let's collapse this down to a normal size. Two of the main take-home points out of this little demo are, one, that these different atoms, these different molecules even, that consist of individual atoms have line spectra as opposed to continuous spectra. Okay, that's item number one. And item number two is that they tend to give you different sets of line spectra for different atoms. So the first point basically establishes that we can distinguish between something that is just an atom and something like a star. All right. The latter, usually you go to black body radiation, black body emission, thermal radiation, that kind of thing to figure out what it's going to do. The second one, the fact that the lines are different for each atom, means that these spectra basically act like a sort of fingerprint for the atom. How do we go about getting these spectral values for these line spectra? Well, in some sense, like I've already showed how you go about this. You essentially put your filter in front of your source, then you look and find where are these located, and essentially the location of each of these lines gives you sort of like an angle, a diffraction angle. So these ones right here might be like the n equals 1 lines. These over here might be n equals 2. These might be n equals -1, etc. And so each of these has a particular location on your camera, for example, or on your detector array. And so graphically, what you basically have is a source like this. Preferably the source is collimated, so either the source is distant, like a star or something like that, or you've done something to collimate it. Maybe you've put like a slit of some sort, and then a lens that can image the slit. So basically you'd have like this, and then it's collimated. Then you have your diffraction grating, which I'm going to draw basically like this. So this is your grating. And then over here you have your detector array. And actually your detector array, if this right here represents a 0-degree angle, your detector array may be like here, for example. At 0 degrees angle, all light has n equals 0, no problem. So your detector is up here. And maybe one line happens to hit here. This would represent theta of a local maximum. So maybe m happens to be 1, for example. So maybe you're looking at theta 1 of your source. You can also, for what it's worth, do this with a prism if you have a really broad spectrum, but usually we just use a grating for this kind. And then you make use of your grating equation, which shows d sine theta m minus sine theta I is m times lambda. And so basically you know the value of sine theta m, that's theta 1. Sine theta I is the incident angle, so if this right here happens to be entering at normal to the interface, this term right here actually goes to 0, then gives you the sort of standard equation that you got from my earlier lectures and likely got from your book or learned in your class or what have you. And so essentially what you then do is, because we know that m equals 1, then we just have lambda is equal to d times sine theta 1. So we need to know what this angle is, and we need to know what the spacing is on the spectrometer. Now the spectrometer that I was using happened to have 500 lines per millimeter, and that is actually equal to 1 over d in millimeters. That means that you're going to get your wavelength for what it's worth in millimeters. So essentially you would just kind of like measure that angle. Now how do you get the angle? Well, this detector is usually fixed in a particular location, and so this distance right here we might call y, and this distance right here we might call L. And so we would basically just use tangent of theta sub m is equal to y sub m over L, and therefore theta m is the inverse tangent of y over L. And so if we're looking at theta 1, we just say theta 1 is y1 over L, where in this particular case, if this happens to be the local maximum, then this is y1. That's where one of the lines happens to be appearing. Now, is a little bit flawed in the experiment that I've done here. This isn't really an experiment. It was just kind of a demo that you can see the lines, because I don't really know like what the scaling is on the computer. I didn't necessarily write down how far away is this source from the CCD and how far is the grating from the CCD detector and so on. I don't really have access to all that. I could in principle figure it out from the values of the line spectrum of hydrogen if they were known. So let's do an example though where maybe we happen to know the value. So before doing the example, I should note that the image that I showed earlier, the screenshot that I showed earlier, was actually for helium. So this one right here is actually for hydrogen. It's still true to say that these are basically your n equals 1 lines, or your, I should say your m equals 1. This is m equals 2. Over here, m equals minus 1. and then kind of off screen would be the m equals minus 2 lines. Okay, so with that in mind, let's go ahead and do our example. All right, suppose we have a hydrogen line, maybe the m equals 1 red line. So all right, we're coming up here, we're looking at maybe like this line right here, for example. Suppose that is located 3.47 centimeters from the central m equals 0 white line. This right here is your m equals 0 white line. So this is m equals 0. That's sort of the center of the screen. Okay. So, and then the screen itself is 10 centimeters from the grating. So we're looking at L equals 10 centimeters, Y1 equals 3.47 centimeters. So this is like Y1, this is like L. And so what we want to know is what is the wavelength of the red line. Oh, again, the grating has line density 500 lines per millimeter. So that is our 1 over D value, in other words. So this right here, 1 over D, we might want to actually convert this one right here into nanometers. These two are okay because they're both in centimeters, and we're going to end up dividing one by the other anyway. 1 over D in nanometers becomes about 5 times 10 to the negative 4 lines per nanometer. So basically what we do is we use that d sine theta 1 is lambda times 1, m equals 1 in other words. And thus we could say something like sine theta 1 is just simply lambda over d. Alright, so that is, or in other words, that means that lambda is equal to just d sine theta 1. And we're trying to solve here for lambda. Need to figure out what sine theta is. Well, tangent theta 1 is equal to y1 over L. y1 over L. So that is 3.47 divided by 10.0. Both are in centimeters, so the centimeters part cancels out. So basically what we're doing is we're taking the inverse tangent of 0.347. So 0.347. So basically we can say that theta 1 is inverse tangent 0.347. If your calculator is in degree mode, you'll end up getting 19.161699. So let's call that 19.2 degrees. Then we can come back to this top equation. Lambda is d sine theta 1. So lambda is equal to d. So 1 over d is this number. That means that d in nanometers, is 2,000 nanometers. Alright, so lambda in this case becomes 2,000 nanometers times the sine of 19.2 degrees. So if I do times the sine of 19.2 in degree mode, what I end up getting is lambda is approximately 657.7. So let's call that 658 nanometers. Now the standard accepted value for hydrogen is about 656 almost 5, like 0.4 something nanometers. So 657.7, we're off by about 1 and change nanometers. That's less than a 1% error if you're doing percent errors here. So not bad. And in some sense, like, that is how you go about calculating what the spectral values are for these. You'd basically just go through for, let's say, hydrogen, and look at each one of these lines and then calculate, all right, for this this one, where is it? For this one, where is it? For these faded green, yellow ones, where are they? Etc. And of course you can also do the m equals 2, you can do the m equals -1, and m equals 1, average them, that kind of thing. And you'd basically just do that for each line spectra. Now, when you buy a spectrometer, it's usually calibrated already so that light showing up at a certain pixel on the camera, detector, whatever, corresponds to a certain wavelength. Now, the pixel width basically also corresponds to what kind of resolution limits are you going to have. So the narrower your pixels, the better your resolution limits, assuming that you're not diffraction limited anyway. The wider your detector array also kind of determines the dynamic range. You do run into problems with this diffraction grating method, which is that the m equals 2 could in principle overlap the m equals 1 if you have a broad enough spectrum. So sometimes a prism is preferred for that. In some sense, like, if you just are watching this as an example for the waves part, then this would be the end. If you're watching this as a transition into atomic physics, or, you know, what else can we do with this, then there's more to be said, but only just. Suffice it to say that you basically can now look at a glowing gas, let's say, and look at the emission lines, and from that determine what the constituent elements in that gas are. So is it hydrogen, is it helium, is it a little of both, etc. Among other things, this is how astronomers are able to tell what things are made of. What is this star, what is this planet, what is this nebula, what are they made of, is by looking at these emission spectra, or alternatively absorption spectra. And yeah, that's about it from the optics side of things. From the atomic side of things, maybe before I go to the atomic side of things, it's worth noting I did take screenshots of each of the gases that I was able to get to basically light up in this little carousel that I have. So I've shown you now 7 of the 8. I couldn't get the water vapor one to work when I was doing these screenshots. From the atomic spectra side of things, there's more to be said, which is that these tend to come in different series. For example, there is what's known as the Lyman series, there's the Balmer series, there's the Paschen series, etc. And these different series essentially correspond to transitions of electrons within the atom, and the series name basically tells us what is the lower energy level that we're transitioning to. So the Lyman series is the first series. That means we've gone from some excited state in the atom to the ground state. The Balmer series means we're going to n equals 2 as our lower state. The next series over, it's n equals 3. The next series over, it's n equals 4, etc. And so it's sort of like the line spectra are known for atoms for these things. In the case of hydrogen, the visible part is transitions to the n equals 2 part of the energy level of the hydrogen atom. For others, it could be n equals 2, it could be n equals 3, etc. The n=1 states for most atoms typically are UV if you're looking at a small atom like hydrogen or helium, and it could even make it into the X-ray range for larger atoms. So in some sense, that's all for today's video. Hope that you enjoyed the demo. I know the video is a little longer than my usual target, but hopefully with the demo in here, this was worthwhile for you. That's all that I was going to cover. I did, however, want to also include, for completeness, some wavelengths that you can detect out of hydrogen. It's actually not possible to have an exhaustive list because these, as we know from quantum mechanics, from the Bohr model and subsequent models of the atom, basically involve transitions from higher to lower energy states, and there's actually kind of like infinitely many high energy states. And so I'm basically limiting to transitions between, let's say, the first 6 energy states. So this would be from the second state to the first state. This is the third to the first, fourth to the first, fifth to the first, sixth to the first. So that's going from right to left rather than left to right. If you want to go from left to right for the Balmer series, this would be 6th state to second. This one right here, so this would be 6 to 2, this would be 5 to 2, 4 to 2, and 3 to 2. This is 6 to 1, 5 to 1, 4 to 1, 3 to 1, and 2 to 1. And then down here, this would be 6 to the third state, 5 to the third state, and 4 to the third state. And there are additional series, obviously, because you could transition into the 4th state or the 5th state, etc. So essentially, the higher the state that you start from and the lower the state you end in, the shorter the wavelength. And as you know, or may know from quantum mechanics, that means the larger the energy difference. So this is your hydrogen spectra, this is your hydrogen fingerprint. And then it became kind of important for things like the Bohr model of the atom, which predicted specific energy values, ergo specific wavelengths in the spectra, and those ended up matching pretty well with what we actually observe. So that's all for today's video. Hopefully you learned something from it. As always, thanks for watching.